Last time, we were in the process of talking about setting up and doing finite element modeling using the CAD system. I think I'm going to back up just a little bit. So we basically started talking about the steps that you will go through on the CAD system to set up a finite element problem, to be able to analyze it and work with it. The first step that we kind of talked about was this notion of creating the model, which you've been in the process of doing. And so the CAD system internally can do finite element modeling. We don't have to go out to another software to do the analysis. It's not like OptiStruct or topology optimization. The reason we left CATIA, the reason we left NX to do topology optimization is because they don't have that module built inside of their software. But most large CAD packages today have some kind of finite element code built internally to them. So modeling and being able to go right into the process is what we're going to examine in this class. So the pre-processing is a series of defeaturing, discretizing the model, assigning material properties, and doing boundary conditions and constraints. Is that the order that you have to do them in? Now, depending on the CAD system, the order changes. In fact, those of you that are on CATIA just automatically will mesh your part for you. You go into their finite element, and as a default, there will be a discretized model sitting in your part tree. Is that something that you would just naturally go and grab and use? And if not, why not? Do we know anything about the element size? Do we know anything about the element type? Do we know anything about kind of how it was created? No, it was just done. And it's been my experience looking at a lot of the CATIA meshes that come up is generally they are fairly coarse. They have not really done a reasonable job of discretizing the model. And so it's sitting there, and you think, well, it's a nice feature, it's there, I don't have to worry about meshing it. Well, you may want to just throw that away and start over meshing. Most of the other CAD packages expect an engineer to set up the mesh and decide the size of element and the order of the element and things like that. You submit it, and after you submit it and get a result, then you have to interpret it. So we talked briefly about kind of, is that, do we want a parametric model? We definitely do. This slide was a discussion of, well, where do we want to do the analysis? Where do we want to do the meshing? In what program? I think one of the things that I didn't mention that I probably should have is, can ANSYS or Nastran do these two products on this side, which are traditionally identified as solvers? They're considered, ANSYS, when you think about it, is a solver. But can they do CAD? Well, they didn't used to be able to do CAD, but they've added quite a bit of CAD. The newest version of ANSYS has a pretty nice CAD interface, and you can go in there and build models, build solids, build surfaces, you can do booleans, you can do all of these different operations. And that modeling that's done inside of ANSYS is done on what kernel? It's done on the Parasolid kernel. So you can actually take a output from NX, a Parasolid output, and you can stuff it directly into ANSYS and get a very good representation. You don't also have a direct reader that's been developed for ANSYS. On the MSC side, can MSC do graphics? Can they do CAD? Inside of Nastran they can't, but they have developed kind of a front end called Patran. Any of you ever heard of Patran or used it? Okay. Patran is a full-fledged CAD modeling program. It is not as popular as NX or CATIA, but it's a full-fledged CAD modeling system. And that can easily be the front end to an analysis package. So these things, the Siemens and the Dassault kind of traditionally started out as kind of a drafting or a design environment. And they have moved over time to where they can now do very nice finite element modeling. The ANSYS and MSC Nastran guys started very much as solvers, and they started moving kind of back towards CAD. So there's a lot of blurring and a lot of overlapping. And at the end of the day, you'll be hired at a company, and they'll say, we do our modeling here, we do our pre-processing here, and we do our solving over here, and it's usually what they consider best in class. What you may want to think about doing is actually benchmarking some of their tools. Because what was best in class 10 years ago and has been labeled as best in class may no longer really be that way.
Along those lines, I have heard that ANSYS is used almost like been a very dominant sort of, there's a very dominant ANSYS element out in the industry because that's generally best in class people where you're educated to do something great so they can use ANSYS. Is ANSYS what we're going to see mostly out there when we get out in the workplace?
So if you're any place other than aerospace, I would say ANSYS is hands down winner. If you're in the aerospace environment, then Nastran is hands down considered the best in class solver. So it's just kind of those two paradigms. Now, if we turn the clock back for just a few minutes and think about an old version of NX, an old version of CATIA V4. If we think about those earlier versions, they had finite element code. The finite element code that was inside of NX was their own homegrown software solver program. The same with Dassault. Dassault had a thing called Alfini that was their finite element solver inside of CATIA. I mention this because in those days, if you held ANSYS or Nastran up to those very basic solvers, you would find out that they didn't perform very well. The accuracy was way off. The speed was way off. Okay? The flexibility, the user interface, all of that were miles apart. Dassault bought a company called Ideas, and Ideas was a first-class finite element company. And the first thing that they did is started incorporating Ideas into NX, and they started leaving their individual solver behind. A year or two after they purchased Ideas, SDRC company, Ideas was the package. A year or two after doing that, the US government stood up and said, Nastran, MSC, you have a monopoly. And what does the US government do when companies have a monopoly? They divide it, right? So they went to MSC and they said, you have to take your code, your Nastran code, a copy of it, and you have to put it out on the selling block, and you have to sell it to the highest bidder. So Nastran was sitting out on the selling block, and guess who bought it? Siemens bought it. Well, it was called Unigraphics in those days. But Unigraphics purchased an exact copy of Nastran. So they now have 2 world-class solvers, and from that day to this day, they have been spending a great deal of time putting those world-class solvers inside of their CAD package and completely walking away from their personal internal solver. Okay. So with that happening and going on, one would have to say, if you go to a company and they say, well, we use Nastran. Nastran is world-class. More than likely, the company doesn't know the history and is not aware that there is a version of Nastran stuck right inside of that. Now, since the purchase, the 2 Nastrans have been on slightly different packages, slightly different paths, but the heart of them, the underlying kernel, is exactly the same. Plus any additions that they've added. Now, is the story the exact same thing for Dassault? They went from V4 to V5. They tried to upgrade their solver, so they tried to improve it, enhance it. It was still kind of being viewed as not world-class. So what did Dassault do a few years ago? They bought a company called Abacus. Have you ever heard of Abacus? Abacus is a world-class finite element program, comparable to ANSYS, comparable to Nastran, just another full functional finite element code. And that right now is kind of standalone, but they are slowly taking that and incorporating it into Cadena. So it's not there yet, but it's being modified and added. So we talked for a minute about defeaturing. We talked a little bit about discretization and the difference, the impact that discretization can do. What you want to be thinking about is, if this is a first run, have it be fairly coarse and look at the values that you get and see if it's even reasonable. Okay? Don't just ratchet down the size of the element saying more is better, because more may just be more bad answers, or the same bad answer, just more refined. Okay, so do a few runs, trying to see whether it's even reasonable, and then begin to dial in by changing the size of the element or increasing the order. Dial it in to where you can get a good solution, an accurate solution in a meaningful amount of time. So we talked about this table and the results of it. I think this is where we kind of left off, if I remember right. What was the issue with the material properties area? What was the takeaway from this kind of a slide? So make sure that they match, but
like ANSYS and that have like really robust material properties and stuff, and we need to fill in all of this to make sure you get it.
Yeah, and I would even say that ANSYS or Nastran, even as long as they've been out there, you can still find that their material property catalog or library may not be complete because of all the new materials and all of the composite stuff and everything else that we're doing. You just need to say, if I want good data, it starts with making sure I have the correct and complete material properties. And so that was kind of the takeaway from this. The next few slides talk about kind of the boundary conditions and the constraints. And you probably can't see this very well here at BYU, so we're going to kill lights. This little axis here is put there trying to represent the fact that we are constraining this entire face. Okay? This little axis in the lower left-hand corner in the center of that cylinder is trying to suggest that we are going to constrain the inside